In the previous lecture, we have discussed about the types of quantization, and we have seen that there are two types of quantization. One is called as uniform quantization, another is called as non-uniform quantization. All these concepts we are covering under the heading of digital transmission of the analog signal. And to continue with that, we are going to study one modulation technique which is called as pulse code modulation. So, pulse code modulation is a technique in which the analog voice data must be translated into a series of binary digits before they can be transmitted. So, pulse code modulation is one of the technique in which the analog signal is transmitted by converting into digital, and with pulse code modulation the amplitude of the sound wave. So sound wave we are considering as the analog signal. So with PCM, the amplitude of the sound wave is sampled at a regular interval and then it is translated into binary number. Again, to remind here, the pulse code modulation technique is the one in which the analog signal is converted into digital, and we all know that when analog signal is converted into digital, it passes through three steps, and those three steps are sampling, second is quantization, and third is encoding. So in the block diagram of the PCM also you will be able to see these steps. The difference between the original analog signal and the translated digital signal is called as quantization error, and we had a discussion about quantization error in the previous lecture. So pulse code modulation is going to use a sampling rate of 8,000 samples per second, and therefore each sample in the PCM is represented by 8-bit sample, resulting in the digital rate of transmission as 64,000 bits per second, which comes from 8 bits per sample, and you are going to sample the PCM signal with 8,000 samples per second. So 8 into 8,000, resulting digital data rate by which the PCM signal is transmitted is 64,000 bits per second. Now we will look onto the block diagram of the PCM system. So the heading is given as PCM transmission system because the upper part of the block diagram is the transmitter and the lower part of the block diagram is the receiver, and in between the transmitter and receiver we are having a communication channel. So let us understand the function of each block one by one. So we have an analog signal which is an input signal which is a sine wave. Let us consider that this particular sine wave is the analog speech signal or any signal which comes from the analog source such as transducer, and that particular signal is given to a band pass filter. So bandpass filter is the first block of PCM transmission system which is utilized for initial band limiting of the input signal, and in some of the books this bandpass filters is also called as anti-aliasing filter. So before passing it through any of the circuit in the PCM system, you should do initial band limiting, and that is why this bandpass filter is there. Followed by that, we are having a circuit of sample and hold circuit, which will be converting our analog signal into the first block. That is analog to digital conversion. First block is the sampling. So sample and hold is going to convert our analog signal into flat top PAM signal. Let me be very precise. It is flat top PAM because we are also having a hold circuit and a sample pulse is provided to this particular sample and hold circuit. So we had studied about that how analog signal is converted into flat top PAM in the video of pulse amplitude modulation. Once the analog signal is converted into flat top PAM, there is an analog to digital converter which comprises of two blocks. One is called as quantization and second is called as encoding. So we had discussion about quantization and encoding in the previous video, and there we have seen that assigning levels to this particular PAM sample or a rounding off to this particular PAM sample is called as quantization. And once the quantization is done, we are going to assign a binary digits or a binary code to each and every sample, and that is called as encoding process. So analog to digital converter is going to convert our PAM signal into parallel stream of data, and that parallel stream of data consists of ones and zeros format. So this ones and zeros format is converted after quantization and then followed by that encoding. Again, quantization is the rounding off of the PAM sample to nearby values, and then once you are rounding off, you have to assign a binary digits or a code to that particular samples or that particular quantized level. Then it is called as encoding. So output of analog to digital converter will be parallel stream of data, but when we are transmitting onto a communication channel, we need to transmit a serial data. So there is a block of parallel to serial converter which will convert a parallel stream of data into a serial block, into a serial stream. And this particular serial stream is going to be transmitted through a communication channel. So you can see it is serial PCM code. Now, if we are considering that communication channel is a long haul communication channel, then definitely in between the transmitter and receiver, there should be a regenerative repeaters which are going to repeat this particular symbol, this particular code as it is, and that is why it is called as regenerative repeaters. Now the signal is received at the receiver. So the receiver is nothing but exactly opposite to that of the transmitter. And the first block of the receiver is receiving a serial data, again converting that to the parallel one. So serial to parallel converter. Followed by that in the transmitter we had analog to digital converter. So in the receiver we will be having digital to analog converter. The signal will be recovered and it will be converted to analog signal, and once the signal is converted to analog signal, we have a hold circuit and a low pass filter which is going to detect the PAM signal and it will convert this PAM signal into the analog signal. So this hold circuit and low pass filter we had studied when we were doing demodulation of the PAM signal. So hold circuits are going to recover the flat top PAM signal, and once the flat top PAM tops are identified, the low pass filter is going to recover the original analog signal back, and that we are calling it as output signal. So this is the complete block diagram of the pulse code modulation. So a PCM code is assigned in the analog to digital converter, and that particular code can be of 2-bit, 3-bit, 4-bit, 8-bit, and that is dependent on the resolution which you want, step size which you want, and that particular code will be assigned, and that is called as encoding process. And opposite to that will be digital to analog converter which will be done at the receiver, and then hold circuit will recover the PAM signal, low pass filter will identify the analog signal. So analog signal is transmitted, analog signal is received, but in between it is converted to digital and then it is transmitted. So that is why this particular heading PCM comes under the category of digital transmission of the analog signal. Now, when we are dealing with the quantization and with the PCM, we had studied that there are two types of quantization, uniform and non-uniform quantization. We said that in the earlier video that non-uniform quantization is always preferable because it gives you approximate quantization, because it gives the same quantization as that of the analog signal. So the companded quantization is the non-uniform quantization which is achieved by passing a signal through a compressor followed by uniform quantizer and then to the expander. So the companding is nothing but consists of three blocks. One is called as compressor, another is called as uniform quantizer, and third is called as expander. So what is the meaning of companding? The companding is nothing but going to assign more number of quantization regions to lower amplitude signal and less number of quantization region to larger amplitude signal. So you can see there is a block diagram of the companding. In the first block, you are able to see there is a message signal which is given to a compressor. So you can see this particular message signal, the compressor is producing similar output that of the uniform quantizer. So you can see this is the characteristics of the compressor. Later on, the output of compressor is given to a uniform quantizer, and uniform quantizer, as we know, it will have a equal step size which is uniformly distributed. And followed by that, we will be having expander. So whatever function has done by the compressor, opposite to that function will be done by the expander. So compressor and uniform quantizer will give us the graph something like this. So the companding process is similar to that of non-uniform quantization. Now question comes that why we are going for companding, why we are not going for non-uniform quantization. So answer is the non-uniform quantizers are very difficult to implement and also they are expensive. So instead of directly using non-uniform quantizer, what we are doing is we are converting our analog signal with the help of compressor to the kind of non-uniform quantization, and then we are giving that to the uniform quantizer, and then followed by that we are having a expander. So companding is nothing but a compressing and then expanding. So this COM and this particular word together is going to form a word of companding. So this is the characteristics of companding. The compressor that is at the transmitter end will have a response like this, which will be similar to that of our uniform quantizer, and the quantization will be uniform, and at the receiver you will be having expanding, which will be opposite to that of companding. With companded system, the higher amplitude analog signal are compressed, that is amplified less than the lower amplitude signal prior to the transmitter, and the non-linearity which is going to be caused in the signal amplitude is to be compressed. So the input to the quantizer will have now more uniform distribution. So two types of companding we are having. One is called as mu law and A law. So you can see when the mu is equal to 0, the response is flat, there is no companding. As the value of mu increases, the companding curve, you can see it is increasing. So mu is equal to 10, mu is equal to 100, mu is equal to 1000. The companding curves are different, and similar to that, you have companding curve for A also. So A-law companding is used in PCM telephone system, and mu-law companding is used for speech and music signal. So remember that why we are doing companding. The companding is going to give us the response similar to that of non-uniform quantizer. But remember that we are not using non-uniform quantization directly. Instead, we are using compressor, and then we are giving output to uniform quantizer, and then the output of uniform quantizer will be again given to a expander. So we said that always the quantization has to be performed non-uniformly, but directly we are not giving to the non-uniform quantizer because non-uniform quantizers are difficult to implement as well as they are expensive. So that is why you are using compressor, and instead of non-uniform quantizer, you are using uniform quantizer only, but output of compressor will be given to a uniform quantizer. So whatever way compressor have compressed the signal, the expander will be expanding the signal. So this is the process of companding which will be used in PCM system, which is nothing but for a uniform quantization.